To understand how the Q of the tank affects the overall phase noise of the LC oscillator, let us quickly take a look at the equivalent circuit of the LC oscillator which we had discussed earlier while looking at the point of view from a negative feedback system. So we had modeled the LC cross-coupled oscillator as two LC oscillators which are connected in a loop. It's called the LCR. Here we are trying to understand the significance of Q tank. As per the Barkhausen criteria, if we want the oscillations to happen, then this loop gain should be such that its magnitude should be 1 at the oscillating frequency and its phase should be, the total phase when we go around the loop should be equal to 360 degrees. So we can write this Lg of S as the gain of one stage and then squaring it, and the gain of one stage is Gm into this impedance of LCR. Gm by 1 by SL plus SC plus 1 by R whole square is equal to Gm square divided by S square LC plus SL by R plus 1 whole square. So if we have to draw the magnitude and phase response for this loop gain, very quickly we can do that. Square L square. So we can see that the loop gain frequency response will be mainly decided by the frequency response of the LCR load. So we can draw the frequency response for the magnitude and the phase of this loop gain as, so the magnitude will look like band pass response. This center frequency is going to be 1 by root over LC. The gain at the center frequency is going to be equal to Gm times R whole square. Similarly, we can also plot the phase. We are already aware that for this LCR tank at the resonant frequency, phase is going to be 0, and at low frequency, phase for the impedance of this LCR tank is going to be dominated by the inductor, so it will be close to plus 90, whereas at frequency much higher than the resonant frequency, this capacitor will dominate, so the impedance phase will be close to minus 90. Since here we have got the square of this tank impedance, so all these phase quantities are going to just double. So if we look at this phase response, then at 1 by root over LC, it is still going to be 0. Whereas at frequency much lower than the resonant frequency, phase is going to be close to 180. Then it is going to drop sharply. It will become minus 180. This is 1 by root over LC. Omega naught. Here it is 180 degree. Here it is minus 180 degree. And we know that the Barkhausen criteria requires that the magnitude at oscillation frequency should be 1 and phase should be equal to 0 or 360 degree. And let's say due to some noise in the system, if the frequency is shifted little bit away from this omega naught, then we can see that there is going to be large change in the phase of the loop gain. So as a result of which now the loop gain will not meet the Barkhausen criteria. So this large phase change will result in a large restoring action for the frequency to be shifted back to the 1 by root over LC. So qualitatively, we can see that higher the slope of this phase response for the loop gain, better is going to be the resilience of the oscillator towards any noise added to the system. So this slope at omega naught helps in gaining constant oscillation frequency. Okay. Steep slope. Now let us try to find out how is this slope related to the properties of the tank. So we can find the phase of this loop gain, the loop gain which we have written. We can rewrite this loop gain as Gm square divided by 1 by g omega L plus g omega C plus 1 by R whole square equal to Gm square divided by 1 by R plus 1 by j omega L plus j omega C, which we can overall square. Here we can do some rearrangement. You can see that L and C both are coming in this expression. So we can rewrite this expression in terms of omega naught. We take 1 by j omega L out. It is 1 minus omega square LC is equal to Gm square by by R plus G omega L 1 minus omega square by omega naught square. That is equal to Gm square. So let's put here. So Gm square R square divided by 1 plus R by G omega L, taking omega by omega naught common. This becomes omega naught by omega minus omega by omega naught. So here we can see that this R by L omega naught is the Q of the tank. And we can just rearrange and write in this manner. Omega by omega naught minus omega naught by omega. Here Q tank is equal to R by omega naught L. So we wanted to write this Lg in terms of Q tank so that we can now find out the phase for this Lg and figure out how are they related. The phase for the loop gain is going to be equal to, numerator will have 0 phase. Denominator phase we can find out as tan inverse of this expression multiplied by 2 equal to minus 2 tan inverse of Q tank omega by omega naught minus omega naught by omega. So if we want to find out the slope of the phase around the omega naught, that is what we started with. So we can make an approximation that this omega is very close to omega naught. So as a result of which, this term inside this bracket will be a very small quantity. Say that phase of Lg is approximately equal to minus 2 Q tank omega by omega naught minus omega naught by omega, when omega is very close to omega naught. Now we can find out slope of the phase d by d omega t is going to be equal to 2 Q tank by omega naught plus omega naught by omega square. And omega is equal to omega naught. Slope of the loop gain phase going to be equal to minus 2 Q tank into, it will become 2 by omega naught. Guys, the slope of Lg at omega naught is equal to minus 4 by omega naught Q tank. tells that the magnitude of the slope is directly proportional to the Q of the tank. So if the Q of the tank is really high, it means that the restoring mechanism to bring the frequency back to the original oscillation frequency will also be working strongly. So which indicates that higher the Q tank, we should expect a lower phase noise. So using the simple LTI analysis along with the feedback point of view, we can find the relevance of this quality factor of the tank into the phase noise of the oscillator. So it means higher Q tank results in stronger restoring mechanism to keep the oscillator frequency at the tank resonant frequency. Which implies lower phase noise. Now, based on the actual measurements of oscillators, a phase noise equation was proposed by Leeson. This is also called as Leeson's phase noise equation. Phase noise equation. As per this equation, the phase noise is going to look like 2 kT by P sig, similar to what we have just derived. But then there was fitting factor F added to account for some extra noise generated by the active circuitry. Then we had F naught by QQ tank delta F whole square multiplied by 1 plus F AF by delta F and log of direct. Okay, so we can see that this equation proposed by Leeson looks somewhat different than what we have derived by simple analysis. So we will try to understand the significance of various terms in this equation. So here F is the excess noise factor, which is added to account for extra noise which may be coming from the active circuitry. And this is a fitting factor which is added after measurements. Then we have this F1 by F. This corresponds to the 1 by F noise corner frequency to account for the fact that at very low frequency offset, the 1 by F noise will start dominating and the roll-off will not be just 20 dB per decade, but we'll start seeing a 30 dB per decade because of the 1 by f noise. So if we plot this Leeson's phase noise, then we can see that at very low frequency offsets, you can ignore this one, and we are going to get a 1 by delta f cube kind of roll off, or 30 dB per decade kind of roll off. When the frequency offset becomes equal to FIF, then this roll off is going to transition from 30 dB per decade to 20 dB per decade. We have F1 by F. And also we can see that when the frequency offset becomes equal to F0 by 2Q tank, then the phase noise is going to become flat without any roll off. Here it is minus 30 dB per decade. Here it is minus 20 dB per decade. Then it is going to be flat. So in the measurements, the phase noise profile looked like as shown in this plot. So the closing phase noise had a higher roll off because of 1 by f noise, whereas at this far off phase noise, the phase noise became flat because the buffers which are present in all the oscillator circuit to take the signal out, their output noise has a flat PSD because of thermal noise, and it directly appears in the oscillator phase noise measurement. Due to for noise. Even though this phase noise tries to capture the phase noise profile which is seen in the measurements, still this is an empirical relationship where this breakpoint from minus 30 dB per decade to minus 20 dB per decade doesn't always appear at the 1 by f corner frequency of the transistors which are present in the oscillator. At the same time, this f excess noise factor is also a fitting parameter. It doesn't directly give any physical intuition about the actual noise phenomena present in the oscillator. For these reasons, there have been some modifications in the phase noise analysis, and we are going to see how we can analyze the phase noise of an oscillator which can explain the measured phase noise behavior while giving an intuition about the noise mechanism which is present in the oscillator.